So hello everybody. So we are in our next class and we are discussing about this real life examples of this plasma applications. So we are dealing with this sludge treatment using plasma, and we are finding that it is in a one-step process. We are getting the sludge treated, and we are not only we not only get rid of the sludge, we get very useful items from that. We are able to recover. So kind of temperature that we are talking about is 10,000 degree kelvins or around that, and we come to our next example. So here what we are showing very two, or rather we are showing three examples in this slide. That upper right corner is plasma spray process, and then lower right corner is the plasma processing of waste using air plasma gasifier, and the lower and the left side what video you are seeing, it is a highly collimated long laminar beam that is very useful for study of material under extreme conditions. So let me tell you the usefulness of these industrial processes using plasma. So you know that we do painting or coating, or we coat our walls with the beautiful paints. So all these things we don't require any high temperature treatment. But suppose something we want to some coating where we want to use very high temperature material which will be able to bear with very high temperature, so that will be thermal barrier coating, and then it will be environmental barrier also, like it will protect the surface from the environmental deterioration. So material like very high temperature materials are usually oxides, and their melting point easily goes more than say 1500 degrees centigrade very easily. And some of the material which are commonly in use are alumina, yttria. Alumina means aluminum oxide, yttria means yttrium oxide. So their melting points are extremely high. But at the same time, these materials are extremely useful when you go for environment which are extremely corrosive and extremely reactant. Suppose you are using a container and you want to hold some molten material inside that, and which is extremely corrosive in nature. It will attack immediately the container, and the container material will contaminate the molten material. So that is what we don't require. Suppose you want to sinter some high temperature material and you are looking for some container. Normal material like say molybdenum and iron, whatever you are using, or say graphite, they may be good for holding that kind of temperature, but uh, what may happen actually, they may not be suitable because they can react with the material. So you will not be able to take out the material from that pot where you are making that material to melt and like that. So what people use coating of say yttrium oxide or aluminum oxide. But if you want to coat that, then the first thing is you need to melt it. And while it is in molten state, you have to apply on the material at high speed so that it impacts on the substance and make a very strong adhesive bond on that. So if that is the case, then what will happen actually, that will protect the surface. But if we want to melt such high melting point material, the conventional technique doesn't work. For example, suppose you go for resistive heating, it can reach a high temperature, but it will not be able to instantaneously melt that material, and it will coat the object that you want to coat. So plasma becomes a very useful technique for that. This is because This is because plasma is having a temperature in excess of 10,000 degree Kelvin, and that can melt any material very easily, but at the same time it can evaporate also because the temperature is too high. So before it gets evaporated, the material should impinge on that substance or the substrate which you want to coat, and then the job is done. So this is a technology which is very technological skill required. High technological skill is required to do that thing, but this is now being used in high-end applications in many places. So one of the coating that is being done on the upper right corner, you have seen the torch, plasma torch is mounted on the hand of a robot, and though that robot is moving as per the program that is made by the user. Then you come to the lower right corner. What you are seeing here, we are using the air plasma torch that you have seen, that you have developed on in the previous slides. We are using the torch to make the hazardous chemical mitigated. This one, this PVC, polyvinyl chloride. So chlorinated plastic, if you burn at temperature say around 400 to 600 degrees centigrade, which is a very common temperature you arrive when you burn that in open. So when you do so, then very carcinogenic compounds like dioxin and furan, so they get generated at that temperature from this kind of material. When you burn at a temperature in presence of oxygen, say temperature around 400 to 600 degrees centigrade, and that is the temperature when you that you achieve when you burn these materials in open atmosphere. Now the problem is that some of the isomers of dioxin and furan are carcinogenic at the nanogram level. And the unfortunate thing is that these compounds are actually solids when they come into the atmosphere. And they are very tiny particles, so they float like aerosol, they spread through the atmosphere, and they comes down through rain. So where you are generated, the particles move far away from there. Of course, that is there at the place where you are generating or where you are burning, but it is not necessary that that is confined to that area where you are burning. So through rain they come down, then they automatically drop down because they are solids, and they enter into the vegetables and they come to the ponds where aquatic animals take them. And when you consume the vegetables or the aquatic animals, then they enter into our body, and that is very dangerous. So this plasma, which is having a temperature beyond say 9,000, 10,000 degree Kelvin, at that temperature all the molecular bonds break. Like suppose you have this carbon and nitrogen, they are benign things, and everywhere there is carbon and our atmosphere is full of nitrogen, but if they combine together, then they form the bond CN, and that is the cyanide, which is one of the most toxic compound on the earth. But the moment you separate C and N, they become benign. The same thing what we do in plasma, because of the very high temperature, that bond breaks, and what we get actually benign things. So that is why plasma is the only accepted method for mitigation of any hazardous material or poisonous material. So for burning of this chlorinated plastic, maybe the plasma is the only solution for burning. Similarly, on the left side, what example we are showing, this is an extremely narrow plasma jet that you are seeing there. It is a laser like jet that is coming, and this is extremely long, and highly collimated. You see that it is not diverging at all. This is has been developed. This kind of highly collimated long laminar beam has been developed in our lab, and these are being used for testing of material under extreme conditions. So that is where this industrial plasma can contribute to the fusion area, because material is one of the major constant of this fusion devices, because you know that fusion happens at very high temperature, and some of the plasma facing components face really very high heat flux, even though you are confining the plasma in the core using some magnetic confinement. So for testing those materials which should be used in such extreme conditions, you don't need to make a fusion plasma device like tokamak. Rather, you can artificially create the situation using such very concentrated plasma beam, which will simulate the situation, experimental situation, that you are expecting under such conditions. So this kind of devices can be used to test material under extreme conditions. So from these examples, actually I am trying to convey you the extreme usefulness of this industrial plasma sector. So they can contribute to very high-end application areas, they can contribute to our society, and they can contribute to even to fusion research, although we are actually not involved with the fusion. Now, so far, the temperature that we are talking about the plasma, it was more than 10,000 degree Kelvin. It can easily go up to 30,000 degree Kelvin for these cutting torches, and typical argon plasma torches can give you temperature around say 8,000, 9,000 Kelvin, and it can exceed easily 10,000 degree Kelvin. And the air plasma torches, very long jet air plasma torches, what we have shown you here, they can reach temperature easily around 8,000 degree Kelvin, and they are very useful for treatment of this municipal solid waste, hazardous waste. And out of that, actually what they produce, that will come later in our course when we are actually go for the applications. And there we will find that they are actually giving very useful items which can be wealth. So basically these devices has the capability to make wealth from the waste. Now the device that you are seeing in this slide, it is a different kind of device. It's totally different from the kind of device that we have discussed or we have seen in our slides so far. These devices, the plasma jet that is coming out, you are seeing here in the video that the plasma jet is impinging on some water in a crucible. And you are seeing that water is not boiling, neither it is evaporating. So practically what is there, that you can touch the plasma by hand. So definitely the gas temperature is below say 40 degrees centigrade, whereas we were talking about the plasma jet which has temperature of several thousands of degree Kelvin. But here the temperature is something so low that you can touch the jet by hand. So this type of devices are called cold plasma devices, and you know that the electron temperature in these devices can reach easily 2 to 3 electron volt. 1 electron volt is 11,600 degree Kelvin, and you can understand what is 2 electron volt and 3 electron volt. Although the electron temperature is so high, still the your heavy species temperature like the gas particles and the ions, their temperature is no more than, say, 40 degrees centigrade in this device. But the interesting part is that it can generate all the ions and radicals which are extremely useful for biochemistry. These types of devices are very useful for biomedical application because of these radicals they are generated, and the gas temperature which they offer is bearable by uh, human cells or biological cells. One of the most beautiful application of these devices is in the cancer cell treatment. Now, tremendous research is going on in this area, and on the upper right corner, the slide that has been shown here, we have applied this jet to some breast cancer cell lines. Here, you can see that just after, say, 300 seconds, you see that almost none of the cancer cells are alive here. Another interesting part which is gradually appearing in these devices, that these devices can selectively kill the cancer cells leaving behind the healthy cells, which is usually not possible using the radiation medicines. But this part is still being explored. I only want to say that such devices are usually called CAP devices or cold atmospheric pressure plasma devices. They find many interesting applications in biomedical area and novel material synthesis area like drug delivery and new drugs, polymerization. So in this area they are finding wonderful applications nowadays, and research in this area is coming up like anything in present time. So what I show here in this slide, that industrial plasma applications starts from novel material synthesis to electronic industries, agriculture, medicine, waste management, then plasma metallurgy, plasma cutting, welding, then physical vapor deposition, chemical vapor deposition, atmospheric pressure, plasma spray coating, nanosynthesis, and as we have seen that material qualification under extreme conditions. At all these sectors, this plasma, what we are going to study, that is cold and thermal plasma, they can contribute. So if you go through the span of use of this plasma in various sectors, you will see that almost at every stage of a life or every moment of a life, whatever we are using, somewhere or other, this plasma is involved. Just now, when I am giving this talk, you can see the fluorescent tubes that are lighting this area, they are using plasma. So, in similar way, actually, we see that at every part of our life, some way or other, we are using some plasma technologies. So, the study of this course will give you a comprehensive basic background to directly work into the area. Maybe it is some industrial sector, or maybe it is some PhD curriculum, or maybe it is some academic activity. All these sectors can get enough preparation of basics and application from this course. So as I told you that plasma covers more than 99% of the visible universe. So these are some examples. This galaxy is a nebula. Our sun is an example of beautiful example of plasma. So also in nature, some other areas like aurora, lightning, of course stars and galaxies, they are all in plasma states. So we start how to get plasma. any example, any body, anything like this pen, paper, even this mouse or this book, just keep on supplying energy. What will happen? Initially it was some solid, then as you give supply energy, then it reaches either directly to liquid state, or it can directly sublimate, or it can go to the gaseous state. Now what you do actually, you keep on heating further. Then what will happen? A time will come when the gas will be superheated and the electrons will be stripped out from that gas. So this is the stage when the plasma starts forming. When you have heated the gas enough that now it is an assembly of large numbers of positive and negative ions together with neutrals, and it starts showing the shielding effect within certain distance, then we say that we have reached the plasma. So basically, if you want to convert any substance into plasma, just keep on supplying energy. A stage will come when the electrons will be separated from the atoms and it will be a collection of ions, electrons and neutrals. If you provide sufficient energy, you may say that all of the atoms are ionized, and we can say that it is a fully ionized plasma. Plasma can not only include these ions, it can of course include double ions, triple ions as well, and molecular ions also. So depending on the kind of plasma and the kind of energy that you have supplied to that. Now some interesting facts about the charge neutrality. You remember that we started with a substance which is actually not charged. Like suppose the pointer I am taking, it is not charged, and if I keep on heating it, a time will come when it will melt, it will evaporate and it will form the plasma. So we started with a neutral object, and no extra charge has been given to that, nothing, neither something has been taken out. So what you find that the ultimate substance which has been created in the name of plasma should be electrically neutral, isn't that? Now this means that what we are getting, it is equal number of positive and negative charges, but they are separated in the plasma state. Now it is a natural question, as I have already told in my previous class, that whether if we go inside and closer to an atom or an ion, then should we see the charge neutrality? Actually, that is not as you can think. Obviously, that if we are very close to a charge, we must see the Coulombic field of that charge, and it should not be anything else other than that when the distance tends to 0. But as we go away from that positive charge, then what we see that volume includes not only the positive charge, also the negative charge within that volume. So you can imagine a sphere within which there will be sufficient numbers of positives and negative ions which can make that neutral. So what is the length scale above which this charge neutrality will be maintained? That is a question. So we'll try to understand all these things in this course actually. Now, why plasma behaves in a different way? It is basically the long range Coulombic force which is responsible for the kind of behavior that we observe. with distance, electric field decreases. How it decreases? It takes the 1 by r square formula. But you just think that number of charged particles, as we increase the radius, then that increases cube of distance. So your electric field is decreasing 1 by r square, and the charge density, that is increasing as r cube. So that is causing the possibility of coherent addition of electric and magnetism of an assembly of charged particles, and the collective behavior of the charged particles basically originate from that. You know that molecules in ordinary gases, they interact through short range forces, and but such collective behavior that is originating through the long range forces, it is naturally you cannot expect in ordinary gases. The physics of plasma is essentially a many body problem, and collective behavior of the charged particles is a very important part of it. Now, plasma, when I am telling, I told you that different kinds of plasma that can be generated, and here in this slide, I am showing you the different kinds of plasma in terms of temperature and density. Basically, temperature and density are the two parameters usually used to characterize any plasma. And you can see in that slide that starting from ionosphere at bottom left corner to the laser fusion at the upper right corner. So you can have a very high temperature plasma in fusion reactor, laser fusion, tokamak, solar corona, and if you want to achieve very high density at laboratory, then you can see that this arcs, electrical arcs, can give you easily a number density of 10 to the power 22 to 10 to the power 23 per meter cube easily when you are going for this plasma generation. Similarly, ionosphere, you can see that the density of plasma is very low, at the same time that your electron temperature is also very low. So we stop here in this class, and then in the next class we will start with the ionization. So how we can ionize and then get the plasma formed, because that will be the basic requirement to get the gas ionized, and how much energy will be required to ionize the gas, that will be a practical concern. So we will start from there in our next class.